This is a continuation of the Chapter 6 review with problem 12. And here we have another triangle that we're going to find the vertices of the mid-segment triangle for. So let's go ahead and bring up that triangle. And we see that unfortunately we were not gifted with easy lines. So we're going to have to find the midpoints of all these segments in order to be able to draw in the mid-segments. So we're getting a lot of practice in finding midpoints. So let's go ahead and let's find the midpoint for DE. So to start with, this is DE midpoint, which will give us the difference of, or the sum of the x's, average of the x's. So -3 plus 3, so -3 plus 3 over 2, and 1 plus 5. 1 plus 5 over 2, which gives us 0. -3 plus 3 is 0, so that's 0. And 1 plus 5 is 6. 6 divided by 2 is 3. So we have 0, 3. Then for EF, midpoint, we have average of the x's, so it's 3 plus 1 divided by 2, and 5 plus -5. So 5 plus -5 over 2. 3 plus 1 is 4. 4 divided by 2 is 2. And 5 minus 5 is 0. 0 divided by anything is still 0. And then the last one, DF, midpoint, is the average of the x's, -3 plus 1 over 2, and 1 plus -5 over 2, which gives us -3 plus 1 is -2, divided by 2 is -1, and 1 plus -5 is -4. -4 divided by 2 is -2. And so those are our coordinates. So let's go ahead and put in those points. So we have, first of all, we have 0, 3. So 0, 3 is our first coordinate, which is going to be right here. Then we have 2, 0. 2, 0 is right here. And we have -1, -2. So -1, -2. Let's go ahead and connect our segments. So we have one from here to here. We have one from here to here. And we have one from here to here. And there is our mid-segment triangle. So now let's go ahead and draw in our coordinates. So again, this was 0, 3. This is 2, 0. And this is -1, -2. And those are the coordinates of our mid-segment triangle. Now on to problem 13. Problem 13 says, describe the possible lengths of the third side of the triangle given the lengths of the other two sides. Now these problems are going to require us to employ the triangle inequality theorem, which says that the sum of the lengths of any two sides of a triangle must be greater than the third side. So let's go ahead and work through 13. So in problem 13, we're going to write down the lengths that they gave us for the sides of a triangle. Now, if we look over to the left of 4, is there a number less than 4 that when added together with 4 will give us a number greater than 8? No, there's not. Even if the number were equal to 4, 4 plus 4 equals 8, and the inequality theorem says that the number must be greater than the third side. So we know that something over here will not work. But we could use a number slightly greater than 4. So this gives us our left endpoint, if you will, for the lowest possible number for the length of our third side. So I know that the length of our third side is going to have to be something greater than 4. So we'll put in this value. Now we're looking for the other number that goes out here. Well, we know that 4, that's going to be some number out here. 4 plus 8 is 12. Well, if these are already the lengths of our two sides, and I stack a length of 4 plus a length of 8, making some straight line, if the other side length, the third side length, were equal to 12, these wouldn't actually make a triangle. So the length that I make has to be less than the sum of these two. So it has to be less than 12. Because whatever I pick for this value, this number plus this number must be greater than 12. And so this gives us the possible lengths of the third side of the triangle for triangle 13. And now let's do problem 14. So for problem 14, in a similar fashion, what we're going to do is we're going to write down our two values. So we have 6 and 9. Give us some space in the middle. And again, we ask ourselves, is there a number less than 6 that when added together gives us a number greater than 9? And the answer is yes. If we take 6 away from 9, we get 3. So if our number is somehow greater than 3, then we will have the lowest possible value for the length of the third side. So 9 minus 6 is 3. That gives us the lowest number. And for the greatest possible number, that number has to be less than the sum of these two values, because these are already the lengths of the sides. So 9 plus 6 is 15. So whatever number I pick has to be less than 15. So the number that I pick has to be less than 15. Because if we take some number greater than 3, add it to 6, we get a number greater than 9. If we add 6 plus 9, this number would have to be less than 15, because 9 plus 6 equals 15. So our number can be anywhere between 3 and 15 for number 4. And now on to number 15. Now for number 15, we have some slightly different numbers. So let's write down 11 and 18. Now, is there a number less than 11 that would give us a number added to 11 that gives us a number greater than 18? Yes, there is. So we take 18 minus 11. 18 minus 11 gives us 7. So our lowest value that it could possibly be is 7. And a number between 11 and 18 would also work. But so would a number greater than 18. So we've got to figure out where that number resides. And we just add these two values together. And 18 plus 11 gives us 29. So since 11 and 18 are the existing lengths of the triangle, the number we pick has to be something less than 29. So our target value can be anywhere between 7 and 29, not inclusive. Now on to problem 16. So problem 16 says, write an indirect proof of the statement in triangle XYZ, if XY equals 4 and XZ equals 8, then YZ must be greater than 4. This is an indirect proof of the use of the triangle inequality theorem. And what the theorem states is the sum of the lengths of any two sides of a triangle must be greater than the length of the third side. So in order to prove that YZ must be greater than 4, using an indirect proof, we're going to initially assume the opposite is true. So we're initially going to say that YZ is less than or equal to 4. Now, in order to use this assumption to prove the theorem, we have to say that by the triangle inequality theorem, XY plus our YZ value is going to have to be greater than our XZ value. And so using our given values, since XY equals 4 and XZ equals 8, we would have the expression 4 plus YZ is greater than 8. That's what would have to be true to employ the triangle inequality theorem. But because our initial assumption stated that YZ is less than or equal to 4, if we put a number in here that's less than or equal to 4, then since YZ is less than or equal to 4, XY plus YZ can at best be equal to 8. If YZ equals 4, then 4 plus 4 equals 8, but it's never going to be greater than 8. And therefore, we have to conclude that our final assumption, our initial assumption was false, and YZ must be greater than 4, thereby proving this statement that we had to prove using an indirect proof. And now on to problem 17. Problems 17 and 18 employ the hinge theorem. The hinge theorem states, if two sides of one triangle are congruent to two sides of another triangle, and the included angle of the first is larger than the included angle of the second, then the third side of the first is longer than the third side of the second. So, here we have RQ congruent to RS, and RT is congruent to itself. QRT is bigger than SRT, which makes QT longer than ST. So for 17, we would say QT is greater than ST. And now for problem 18. Problem 18 uses the converse of the hinge theorem, which states if two sides of one triangle are congruent to two sides of another triangle, and the third side of the first is longer than the third side of the second, then the included angle of the first is larger than the included angle of the second. So here we have the same triangles. Since QT is greater than ST, so this is bigger, this is smaller. This side, this angle, must be bigger, and this is smaller, which means that the measure of angle QRT is greater than the measure of angle SRT. And that wraps up Chapter 6 review, and I will see you in the next session.